guess I was sort of introduced. Yeah, I'm Peter Goodman. I'm from a company called Trail of Bits, a software security company. And the title of my talk is Can Symbolic Execution Be a Productivity Multiplier for Bug Finders? I'm a staff engineer at Trail of Bits. There's also two other Trail of Bits employees here as well. There's Boyan Milanov, who's the creator of the Symbolic execution engine. So by all means, talk to him. And there's also Henrik Lauko right over there. And he's developed something called LART. I don't even remember what it stands for, but it's also like a symbolic model checker thing. And he's, face palming right now. Feel free to reach out to me if you're interested in any of these topics by email or by Twitter. And if you want to hear about like any of these things, which are my, any of my interests, I will talk your ear off about these topics. But anyway, let's move on. So today's talk is about productivity tools, really what makes a bug finding system or a bug finding tool a productivity multiplier for bug finders, for human bug finders. And so I've broken this sort of down into three parts. The first is sort of what I consider to be the three pillars of a productivity multiplying bug finding tool. And I'm going to sort of provide some exposition on those three pillars by talking about how today's open source symbolic executors sort of measure up in terms of these three features. Then I'm going to bring it back to a KLEE focused sort of center and talk about my pet issues with KLEE and how I think KLEE could improve today to address some of the issues that it has and where I think KLEE could go sort of in the medium to long run to really improve. And then finally, what I'm going to talk about is why I think MLIR is really the future for program analysis. And a big part of that is, and a reoccurring theme throughout this talk is that, being like there's the analysis domain on which you operate. In this case, for KLEE, it's LLVM. But then there's the domain on which bug finders care about, which is often source code. And there's a really big gap to bridge there. And so I think MLIR will help us bridge this gap. So let's go on. The three most important things I consider for an effective bug finding tool is composition, is comprehensiveness, and transparency. So composition, I'll break it down into sort of these two things. One of them is internal, and that's sort of like, if the tool gives me a result, can I leverage the result to get more results? The second one is really about taking your blinders off or not having tunnel vision and realizing that you're not using these tools in isolation. There's some larger workflow that the bug finder has that you want to fit into. They have a process that already works. And if you're going to make a tool that they're supposed to adopt, then you better fit into that process or have like something really compelling that will make them want to adopt that. The other issue, or the next pillar, is comprehensiveness. And I make a pretty bold requirement here of 0 false negatives. And really that's aspirational. It's not like, it's almost impossible to reach in practice. But I would say that bug finders can have a higher tolerance for false positives than you might realize, especially if those false positives bring them to interesting places in your code base. Because when you're auditing a code base, you already have to look at the whole thing anyway. And so making sure that you don't miss things is really important to be able to trust the tool. The last issue is transparency. And so transparency is really about, do I understand how the tool is behaving? So the behavior should be predictable, the results should be explainable, and the limitations understandable. And this kind of goes hand in hand with comprehensiveness. You're not always going to get, you're rarely going to get 0 false negatives, but if I can understand sort of the scope of the limitations, then that's really going to help me want to use a tool. So I'm going to start by focusing on composition, and that's where I'm going to compare other tools. So I've got a scatter plot, and I've placed the tools how I think they should go, and a bit of context as to sort of what matters or doesn't matter to me is that the workflow is very important for how I've placed these things. So we can see like there's a bunch of these binary symbolic executors, and they appear pretty high in the top right. And that's because a lot of them fit really well into the workflow of reverse engineers. And they've really optimized for that. And so like they're being used, they work, they have good composition. The other thing is I don't measure or how a symbolic executor performs in terms of like code coverage. That does not affect the, how I've placed these on this scatter plot. Like if you compare favorably against, if your symbolic executor compares favorably against a fuzzer, it's not particularly inspiring to me. It's, there should be some significant advantage above and beyond a fuzzer for me to want to adopt a symbolic executor. And so that, that isn't even affecting this. So I'm going to go into a few of the tools. Carnegie Mellon and Stanford. You've got BAP and SIS, and I think these are two really interesting tools, and they've got some of the features that I think future symbolic executors should have. BAP has this knowledge base. It's got this this like a persistent representation of knowledge learned throughout a symbolic execution. It's got this concept of mutual fixed points, so that you can derive new knowledge based off of this. I think it's a very powerful feature that's missing elsewhere. And the sort of way it's been structured is to make sure that you use it properly. And what I think is very powerful about SIS is that it's sort of it's basically a variant analysis and an under constrained symbolic execution engine. And so it seems to have nicely addressed the scalability story in terms of large programs. You first do the rough pass that filters out the interesting places, then you apply to those. Next up, we have the binary symbolic executors. There's Manticore, Anger, and Triton. And I've kind of got them broken down into two groups here. In terms of all of them, they all have a Python API. And to me, that's really important because what are you using for doing reverse engineering or deobfuscation or any of that? You're using Binary Ninja, you're using IDAPRO, and you might be using Ghidra, but you're probably using IDAPRO or Binary Ninja. And those all have a built-in Python console. They all have excellent support for Python APIs. And so these tools have all really optimized to hit those points and integrate nicely. And so that means that they can compose well with the APIs available in those tools. I've separated off Manticore from the others, Mott, Anger, and Triton, because I think what makes these other tools more powerful from an internal composition perspective is that the way you can hook them, it provides you more control, provides you more leverage. And I call these like actionable callbacks. You can say, oh, tell me when a register or memory is about to be written, but then you can change what gets written. And that will influence the rest of the symbolic execution. And that's a place where the bug finder gets to impose their will or their interests on the process. And I think that is highly valuable to enabling bug finders to kind of explore the programs in the way that they want to. The elephant in the room, KLEE. I think I'm going to quickly go over it. I think the superpower of KLEE is its runtime. And that's like that sort of where the KLEE libc thing lives. It's linked against your target program. The whole middle section is basically just talking about the runtime. I think there's missed opportunities in the runtime where it could go way further. And then there's places where KLEE does way too much. I think stepping back, though, a big issue with KLEE is that it tries to sort of be a whole program executor. It generally tries to start from main. You have to have all your bit code all up front. And for most, like for interesting targets, they're already well tested. And I don't want to run them from main. I want to run them from some part of the code that I'm interested in. I want to start in the middle of the code. It could be at a function. It could be in the middle of a function after billions of iterations of a loop. And so KLEE is not a tool that is as amenable to that workflow. It feels more like you push a button and you run it and you let it go, and maybe magic happens. Lastly, we have or maybe not lastly, we have the combination of S2E and SimQMU. S2E, Leslie will maybe talk about it. I think the most powerful thing about it is that it seems to be able to run on anything and everything, which is not something that you can say about most tools. Like if you have a closed source Windows driver, you know, if you put the effort in, you can run S2E on it, and that's extremely powerful. And a thing to note though is that putting the effort in to get, you know, doing work to get work done, that I don't consider that a downside. In fact, that's already how, you know, like if you're analyzing a whole program, if you're auditing a whole program, you're doing a lot of work. The best usages of binary symbolic executors require tailoring them to your target. So putting the work in means like you're already thinking deeply about your program, the target, and the types of bugs that you want to find. And so that's sort of why S2E ends up in the middle. I don't see the effort it takes to get it working as an issue. SimQMU, it's sort of down at the bottom. I'm not entirely sure what to think of it, to be honest. It seems to be like the best and worst of 3 systems combined. I don't know if it's maintained. I feel like it could be pretty good. And then lastly, there's SimCC. I feel like SimCC hasn't reached its potential. That's why it's sort of way down in the bottom. It looks like it could be a really good unit testing framework piece. Like it's basically a sanitizer is how I see it. It's like DFSAN combined with a symbolic runtime. That's what it looks like. And I think it could be great for property testing and unit tests, but it doesn't really seem to provide much additional sort of value beyond fuzzing or integrating with a fuzzer. Pointing to the 2 pillars, comprehensiveness and transparency. This is where I think everyone could use more. So why do I say this? It's really that, I mean, you know, not everything is the static symbolic executor, dynamic symbolic executor. There's, you know, that whole spectrum. But I think when it comes down to it, something like KLEE or Manticore, those are static symbolic executors, and you know, apparently they are comprehensive. They say they will explore all feasible paths. In practice, they're not. You have path scheduling, and if you suffer from path explosion, then sure, maybe you can represent all of the all the states, but some states are just never going to be, you know, like you're gonna like run out of patience, and you're never going to see those states. Or you have a state pruning heuristic, and that state pruning heuristic is just going to throw away things. Or you have some sort of issue in the solve where, you know, like maybe you just don't concretize certain, you don't concretize certain things because you say, oh, I visited already. So these are all places where really you're actually not being comprehensive. Symbolic pointers for transparency. I think any symbolic execution engine, they make some sort of choices about memory access. Like, symbolic reads, or reads through symbolic address, writes through symbolic address. Every engine makes some sort of implementation choices, and these implementation choices limit what is actually expressible. And I'm focusing on dynamic symbolic executors here because, and so like I think in terms of like SimCC, for example, because it's not entirely clear, you know, like, okay, you record the path constraint, you invert some conditions, but what was the effect of that on some symbolic memory accesses? It's not entirely clear at all. So overall, I would say every implementation is just chock full of heuristics, and these heuristics reduce comprehensiveness somehow, and they reduce transparency somehow. This is expected, it's not surprising, but it's just something to be aware of. So I guess I would describe heuristics as, you know, they're the short-term gain, but they're the long-term pain. You know, you can publish a paper about a heuristic because it's novel, but from an adoption perspective, a heuristic, to me, it just looks like a big risk. Like I see, oh, you know, we have this novel strategy, it maximizes coverage against a fuzzer, oh, great. But what does that mean for my target? Like if I run your symbolic, if I run your symbolic executor with a heuristic on my target, is it going to miss bugs? Like, do I have to go and double check everything that's found? Like that is a realistic concern if, you know, if we're looking for bugs, and especially if we're looking for vulnerabilities. And so I think the way to look at heuristics is that the more heuristics you put into a tool, the more kind of the more that tool internalizes its own agency. Like it kind of, your heuristics are going to interact in funny, unpredictable ways. And so it's going to make your tool unpredictable. So now we've talked about the 3 pillars of productivity, sort of productivity, but really about like what I think makes a good bug finding system. Now I'm going to talk all about KLEE. So let's get into it. I mentioned earlier that I think KLEE's runtime is its superpower. And so just to set the stage, the runtime is sort of like where that's where KLEE libc is. It's where you would put your system call models. It is, you can like, if you see people put examples of like KLEE makes Symbolic, that's all code that exists in the runtime. And that's compiled to LLV and bitcode. And then your target is compiled to LLV and bitcode, and the 2 are linked together. And what's really cool about KLEE's runtime is that the symbolic interpreter interprets both. So not only is it going to fork down branches in your target program, but it's also going to like fork on the inside of your system call model. And I think that's like really special. And I've never really seen that in other symbolic executors. And then there's sort of this escape hatch in the runtime called these special function handlers. That's how KLEE makes Symbolic works. You can call out to the interpreter and in theory do stuff like make a new symbol or maybe get data from the outside world. And so that's really cool. And then probably the most interesting thing though about the runtime isn't just like the forking. Like the forking is cool. But the most interesting thing from my perspective as a bug finder is that I can include the target program's headers. And so I can directly interface with data structures in the target program. I could call functions in the target program. So it's like you can kind of start matching up with the sort of domain of the program. And that's where things get really interesting. Despite the runtime being the superpower though, I think it's underpowered or like it hasn't gone nearly far enough. And so I think what's happened is that this sort of trick of symbolic interpretation on the runtime code or on your target program forking has led people to believe they're actually doing, actually checking properties or actually maintaining properties. Like you say, oh, in my runtime, I do an assertion, and then if that assertion, if that condition is symbolic, then KLEE will fork down 2 paths, and then maybe I can cancel out the state or down one path or error out, and then down the other path, that condition, I know it's true. I know it's true in the rest of the path condition. And so you're like, yeah, Peter, I tested the property, I evaluated it, it's guaranteed to be true for the rest of the time. But what I'm really interested in is having a persistent record of properties that were true. And so this is something where I think you can kind of already see it in KLEE today, where when you say KLEE makes Symbolic, you use like string formatting to name your symbolic variable like, oh, standard in _0, standard in _1, that type of thing. And I think really what you want to do is you want to say input is a property, and here's the symbolic data to it. Or there was this malloc, there was this free. And I'm going to give an example in 2 slides for like that tries to make this a bit more explicit what I mean. So I'm going to try to get there. But really, I want to be able to say, in the middle of symbolic executing, I should be able to retroactively ask what properties were true. I should be able to compose properties and say, was this property and that property true? Or given a symbolic variable, can I connect these 2 properties together? And that would help derive new properties. The ideal situation is that you start moving logic out of the interpreter and into the runtime. So that touches nicely, because I think right now the interpreter or KLEE proper kind of does too much. Like it sort of does everything. I think we can agree that it's grown organically. It's got a lot of ingredients that are very, very sophisticated, very interesting. But it's also kind of suffers from maybe paper-driven development, where over time, you say, oh, I got this great idea, I'm going to publish it and then merge it into KLEE, and now I have a bajillion options. Who knows what they all do? Some of them get merged, some of them don't. And then, so ideally what I would like to see, or where I would like to see KLEE go, is as much as possible externalize, like anything that could involve a heuristic, externalize that. So, like, I mean, go to like a pretty crazy extent. And like I see storage to memory, loading from memory as an externalizable policy. And I didn't do a good job of communicating that in this slide. So if you're reading the slide, it's not well communicated. But really, I would love for you to ask me about this after if you're interested. But the type of thing that I would like to see is that when KLEE wants to do something like store to memory, which is something where you would reasonably want heuristics, depending on like, oh, symbolic memory reads, symbolic memory writes, that type of thing, where you would say, oh, policy, go store to memory. The policy handles it. You can have a default implementation, but I would love to be able to specialize that and proxy it and refine what that next policy is getting, or change it altogether. And my example coming up has an example of sort of what a policy could look like, plus what properties could look like, and how I would love to be able to collude between the runtime and the interpreter. So this is all just like make-believe code. I just wrote it up, and the point of this code is that I want to detect type confusion in Python. Right? Why did I come up with this example? I'm not too sure. But it's an interesting property. So it's sort of like the property we're trying to say is like, okay, let's talk about type confusion in C++ as a basic example. Normally you invoke a method, and then that happens to go through like a virtual table, and that figures out where the actual method is. And type confusion can happen where maybe you free the memory, it gets reallocated, and so you think you're calling method A on some object, but that vtable pointer has changed, so you end up calling method B on some different object, and that's type confusion. And so in Python, the way that might manifest is that Python's sort of PyObject maintains this OB type field, and the OB type says this object has this type, and on this type we have all these class members. And so after you allocate an object in Python, OB type is essentially constant after initialization. So the property here is that I want to claim that after I've initialized OB type, it is going to be constant, as in it is not going to change. And so I've invented some syntax that feasibly could compile, where I say constant void pointer, like this, whatever, pointing at this memory, it should be treated as, I'm trying to claim this should be constant. And I have another property here, changed constant, where I'm saying, okay, this pointer, it should be, it represents something that was constant that has been changed. And again, more invention, we have these wrappers. So the first wrapper of interest is, I invented the syntax, it'd be lovely if you could support it, we say like, okay, we're gonna wrap this PyObjectInit function, and this is the code, like PyObjectInit is a function in Python that initializes OB type. So once it initializes it, it should be constant thereafter. And then I invent this, oh, if we call constant, then that's like saying, save this property. Mark this pointer as constant. And then it should be the case that anytime we're calling a method, so when we're wrapping the PyObjectCall method, that both the type is known to be a constant and that it hasn't changed. And so this is an example where constant is something where it's like metadata. It's like shadow memory in a sanitizer. It's a property that persists throughout the execution. And technically, you could implement this in the runtime. I know you can do this, but it would be awful. It wouldn't have good internal composition because you'd have to implement it as like a set or a hash map, and then you would have to interpret the implementation of that, and that you wouldn't be able to combine those nicely. And so over here, what I have is this example of, here's how I would want to be able to externalize things. I would like to be able to interpose on stores to memory. I would like to be able to ask, does a certain property hold? If that property holds for the address to which we're storing, then derive this new property that the constant has been changed. This is the type of thing that I would like to do, and then defer to the next policy that probably implements storage. So this is sort of my idea, my personal pet ideas of where I would love to see KLEE go. I mean, you don't need to agree, obviously. You should though. It's a bit of a funny example. Anyway, beyond these small things though, beyond these, and they're not small, but beyond those specific, make properties a real first-class entity, and beyond externalizing heuristics as much as possible. Where I think KLEE needs to go is to support interaction with humans. And so that's really challenging because most LLVM values are basically meaningless. Like they're not really related to the domain of the bug finder, which is source code. I would love for KLEE to be very flexible. And so I would say like any constraint, like sometimes you want under constrained, sometimes you want over constrained, sometimes you want just totally concrete. Like I want to just be able to, like, as a bug finder, it's sort of like, oh, I start here and then I start drilling down on a path. Like, it's just start anywhere, not start, just start at main. And then the last thing is be dynamic, like handle large programs. It's brutal to try to have to materialize every single LLVM module via LLVM link into a single module in memory. I have plenty of ideas on how to actually address this, but that's beyond the scope of this talk. So going forward, I think MLIR is the future, and that's going to seem like a bit wild, but there's actually a link to KLEE here because MLIR has an LLVM dialect, and so this sort of the theme here is to say that analyzing LLVM, it's still a good thing because it's efficiently analyzable, but how do we talk back to humans? How do we talk to bug finders? And it's important to have good provenance, and MLIR is something I think that can get us there. So far, I think LLVM has been this like blessing and curse. It's a blessing because it's permissively licensed, and that's been great for both academia and industry. It's caused a lot of momentum. You can get a paper out of an LLVM pass, or at least you used to be able to. It's reasonably simple. Like there's not that many instructions, so you can generally scalably analyze it, and it appears to have reasonable debug information. Like some values can be related back to source code locations. The curse is that really, like the second you kind of go deep into LLVM and start like playing with it, you realize there isn't just one LLVM bitcode dialect or IR dialect. There's many. Every single optimization level is essentially its own dialect. It's full of architecture-specific or target architecture-specific intrinsics. Ignoring those, even before the process of producing LLVM bitcode, like the way Klein does it, makes decisions, target architecture-specific decisions that affect type layout, that affect the types of instructions that you see, and the metadata that you have in your module affects optimizations that trigger like different behaviors for different target architectures. So like what you look at in bitcode, like your bitcode might look one way on x86, another way on x86-64, and a totally different way on ARM, and it's just wild. There's no like uniform like look for LLVM bitcode, especially where types are represented, especially where type representation is concerned. I said this before, but LLVM values are just mostly meaningless. The second you apply the optimization passes, like I don't want to have to look at results printed in terms of LLVM values, because what am I going to do with that? Like, oh, great, it's got phi in there, it's got skib, it's got sroa. Like, what are those? They're not really related to the high-level types. This also applies to like in source code, you have like abstractions, like vectors and such. But in LLVM bitcode, you don't really see those abstractions anymore. They've been inline, optimized. They might have been hoisted. They might have been sunken. They've been specialized, folded, all these things. And so like it all looks very different from like the actual source code that you're looking at. Finally, legacy. LLVM is legacy, but also all the tools built on LLVM are legacy. I bet you a huge number of tools are never going to work on modern versions of LLVM that have opaque pointers because they make so many assumptions that pointers are typed and that there's bit casts with typed pointers. Another thing is just lots of apparently great tools are just stuck on really old versions of LLVM, and there's nothing anyone was really willing to do about that. So that's too bad. Hopefully, though, what you're getting out of this is that LLVM, it's a blessing and a curse. Sometimes it's really great for your application, and sometimes it's not as great. And so the takeaway here is that there's no perfect IR. Like it doesn't exist. There's no one IR that's good for things. And if you're familiar with like the end-to-end process of exploitation, then also this should be obvious. You might have like buffer overflows. You might be able to find them in one representation, but your analysis might miss intra-object buffer overflows because you're either at too low of a level where you can't see the sort of distinctions for where one object ends and another object begins, or you're at too high of a level, and so you can't see that, oh, I could buffer overflow one object and override another. You just don't know that they're beside each other in memory. So like no level is perfect. If you try to kind of handle the whole problem at one level, you're going to compromise your comprehensiveness. So what I think is that there's benefits and drawbacks to each level. High level, you're closer to the domain of the bug finder, but it's very verbose, so you don't have that efficiency. Medium level, I don't really know how many of them exist today. Low level, efficiently analyzable, just like LLVM, but wrong domain for the bug finder. And then binary is sort of special because it's super low level, and yet it's also like if you're operating on binaries, that's the domain of interest. So it's a good fit actually. But there's certain things that are very hard to do at a binary level, like buffer overflow detection. You might not know where one buffer begins and ends, that type of thing. You've got the problem of type inference, control flow recovery, and variable recovery, and these are all like combined problems. So, kind of looking at the stack again in a different way, as you go down the levels, you get more efficiency in your analysis, but the lower you get, you lose your ability to kind of reason about these higher level abstractions, which might help you find logic things, for example. You need to be able to descend the level of abstraction in order to actually implement real exploits. Like real exploits cross the semantic gap from high level to low level. They're not just, sometimes they're at one level, but oftentimes they really require precise thinking at a lot of levels. And as you go lower level, you can often be more faithful to how your program is actually going to execute. So I think, this is my pitch, is that bug finding needs full stack visibility. You need to be able to operate on all these levels. And that's why I think MLIR is the future. We're not there yet. Like MLIR doesn't just come out of the box ready to give you this. But Henrik over there has created this tool called VAST. And VAST, which we recently open sourced as Apache 2, it starts at a Clang AST, and then it creates something called our high-level MLIR dialect. And that's very faithful to what's in the source code. Like if you had type def time t and you care about Y2K all over again or something, then you can actually see that time t is used in the high-level dialect. That's not something that you can easily see in LLVM, for example. And what VAST can do is it can progressively lower down to the LLVM embedding within MLIR. And so I think what's really the opportunity for future program analysis is that we can take something like KLEE, some of those ingredients from KLEE, we can run them on this LLVM embedding with an LLVM-IR, but we should also be able to pop out higher levels and talk to humans. They're like, oh, we got this induction variable and it's symbolic, but it's this meaningless LLVM value. But when I ascend the sort of provenance chain of dialects, here's what it is in the source code. So tell me how to concretize this, or tell me what to do with this, and then kind of bring it back down to low level. I think that is where, at least in interfacing with bug finders, where tools should go. And I'm pretty excited about that. So finishing up, this is sort of a nice summary of this talk. So bug finders, they already have a workflow. Don't ignore that, please. If you're asking bug finders to use a tool, comparing like a new tool that only makes, say, marginal improvements over a fuzzer, that's not super attractive. But if if you're providing a huge amount of value, even if you've got high false positives, or maybe even if you have false negatives, if you have a lot of value to present, then that can be good for integration. It's really important to compose with the tools that they're using in their workflow. So be able to, like, okay, maybe you don't need to solve the whole problem. Maybe they have something else, and then you can consume it and then improve those results. Or maybe you produce results and those benefit other things. That's sort of keeping in mind the workflow. Comprehensiveness and transparency, I think, those are really important to sort of informing you on whether or not your tool is actually going to be adopted. Focus on producing results in the domain of interest to the bug finder. So most bug finder are operating on source code, or they're operating or they're reverse engineers and they're operating on binaries. So we've seen that symbolic executors like Anger, Manticore, Mock, and Triton, they're actually quite successful, and that's because they're already on the right domain. The results are in the right domain. Their analysis is in the right domain. Something like KLEE, its analysis is in the LLVM domain, but really you want results in the source code domain. I wish KLEE would get first-class properties. I wish KLEE would externalize its heuristics more and kind of work towards something like a libKLEE, something that I could extend in my own way and start injecting my own decision making via specialization. And the last thing to take away is just bugs kind of happen at all the levels, or it's really important to see how bugs cross all the levels. And one, hopefully, tool that everyone can adopt is VAST. You don't need to adopt it, but it's worth looking into. And yeah, that's any questions?